So that's the gist of the experiment they did here. But I want to tell you about other activity that's actually going on in the world of gravitational waves. Here we are at the ground-based interferometers, where they're detecting frequencies on the order of 100 hertz or 100 cycles per second down here. And we have all these other potential emissions that are sampling gravity waves at much, much lower frequencies, but much higher amplitudes, all the way on up to looking at the cosmic microwave background radiation, which I talked about, I guess it was about a year ago or so, where it looked like we saw hints in the cosmic microwave background radiation, not a direct detection, but one inferred by the polarization in the cosmic microwave background radiation of gravity waves that were running around the universe at the Big Bang. And that would have been a very significant discovery, because not only does it show that the gravity waves that we could measure here at this particular time, but it also shows that gravity is a quantum phenomenon, that just like light is a wave, but it's carried as a particle called the photon, that gravity would be carried by a particle called the graviton. Anyway, we haven't discovered that yet, because they eventually found out that the signal that they measured in that data could have been due to dust in our own galaxy. So they're still working on that, but that will be a very, very exciting find if we can detect what these are called B modes in the cosmic microwave background radiation. I want to talk to you a little bit about another really cool technique. We've got several experiments called pulsar timing. And these will look at really supermassive black holes in like the centers of galaxies. We know of some systems out there that have two big black holes in the center of galaxies, and that they may actually collide. And so what is this pulsar timing thing? Well, first, there's a couple institutions that are doing. One is what they call the North American Nanohertz Observatory for Gravitational Waves. It's using a couple of radio telescopes. It's a U.S.-Canada consortium. This is the Arecibo telescope. If you've ever seen the movie Contact, it's the one's featured in there. It's a radio telescope. And this is the Green Bay telescope in West Virginia, that utilizing these to actually measure pulsars. And there's another consortium, the European Pulsar Timing Array, and they have a suite of radio telescopes as well. What are they measuring? Well, they are measuring these objects called millisecond pulsars. They're not ones in, they're in binary systems and everything like that, but they have been spun up to a point where they're rotating very, very quickly. We're talking a neutron star, again, something the mass of the sun squeezed down in the size of Denver, spinning on its axis on the order of 1,000 times a second. It's mind-boggling, but they're very, very accurate clocks. So for this particular object, and I can't remember what pulsar, millipulsar this is in milliseconds, 1,000th of a second. This is its frequency there, or the period that it takes to go around, and it's known to that accuracy. Okay, that's this 5 over here, plus or minus 4 from that. Okay, 1 in 18 parts of a second, 10 to the 18 parts of a second. It's very, very accurate. So what they're doing is these very, very accurate clocks that are going on. We know of several of these millisecond pulsars that are distributed out in the Milky Way galaxy, and we can measure their timing there. So the other thing that a gravitational wave does is as it passes, it squeezes space and expands space, but also squeezes and expands time. So these pulsars will actually change this number. So we have a very accurate measure, and as we watch their deflections, we can use the entire galaxy as a way of measuring gravitational waves. And it's a direct detection of those gravitational waves. We actually thought that this particular technique would beat out the technique of the LIGO, the ground-based ones, as the first detection. I was kind of reading some articles written about 3 or 4 years ago, and that's what the prediction was, but obviously didn't pan out. So they're still looking at maybe 2 or 3 years before they have the sensitivity to measure to pulsar timing, using pulsar timing to measure gravitational waves going by. So the other one that I wanted to talk about here was the space-based interferometers, that taking basically LIGO and bringing it out into space. And so the big mission that is currently on the books right now is the Evolved Laser Interferometer Space Antenna, or ELISA. It used to just be called LISA. It was a U.S. and European collaboration, but about 3 years ago, we bailed on that. We couldn't support all the missions that we had, and so the European group basically found another mechanism of funding, and so it's going to be launched ultimately by a European spacecraft. We are still partners in that arrangement there, and this is another one of these very incredible devices. It'll be like the LIGO up in space, but before we get there, we had just actually, there's something called ELISA Pathfinder that just launched in December of last year, and it has gotten to what we call L1 orbit, which is an orbit between Earth and the Sun that goes around the Sun at the same rate, that particular point in orbit, the same rate as we go around, in other words, 1 year. And it's a very stable and pristine point of space. And this ELISA Pathfinder is a technology demonstration just to see if they can create this space-based interferometer. And this is kind of looking into this device, and the test experiment is basically we've got these two cubes, and I'll show a picture of a real cube here in the next slide here, but they will float around in these chambers. And so they're developing this ability to use these microthrusters to put these in space, and as the spacecraft's orbit, these will essentially just float there. And so the lasers go back and forth here, and just like the LIGO experiment, you are seeing how well you have positioned those mirrors so that they're actually not moving. Now, this won't be able to detect gravity waves because these mirrors are obviously very close to one another. They don't have a long enough path length, but they will check the stability. Can you have these mirrors stay still and not produce any interference? So when you do the interferometer, when they combine and you get zero signal, it should just stay zero signal. If you get any fluctuations, you get an idea of how much noise you have associated with that. So these are like a gold and, what is it? I don't want to say platinum, but I'm not sure, alloy. They're about a couple inches on the side. They have these little kind of holders right there, so when it's flown, they first hold that and then they have to release it. And so just this month they have released both of these masses, and they're now freely floating. So everything is looking good, and so they'll be starting to take measurements on this. So when LISA's actually flown, there's going to be 3 of these things creating this big interferometer in space, where they're showing it like it's orbiting around this, supermassive black hole, but it's obviously going to be orbiting around the sun. And I'll show you a really high-tech little video here in the next slide here of this particular mission. It's kind of like a preview for a really good movie and everything. But these are going to be millions of miles on a side, is how they're going to do that. And they were to detect these things of other kind of supermassive black holes also colliding. It kind of spans between what the pulsar timing does and the LIGO measurements we're doing. It's just very dramatic music. So and its sensitivity will be so much better because they're free-floating objects with not having to tie it down to the Earth. It just blows me away the technology that's involved in trying to do this. But you saw with LIGO, it took 20 years to ultimately accomplish that, and the you just got to keep on plugging. Now, this mission is really not designed to launch with the ELISA there until 2034. So it'll be a few 60 minutes before I can report on that data. So this kind of this slide here just kind of shows where we are with those different measurements. So here we are with LIGO here and its sensitivity with this last advanced LIGO that it had put in. And so there's going to be a lot of things probably coming out here in the next year, because like I said, they detected this one. They were still in their engineering run. They hadn't even really officially turned on, and there's probably a lot more stuff that's buried in their data they're looking at, and it's currently shut down to do some improvements. And it'll get down to this point here. The detection level of that other one was actually up in here for the one that they had. So they're well above that. Here is where LISA's going to operate, and its detection level is down here. So these are galactic binary, I forgot all the acronyms that are in here. Here is the nanograv, which is the one that does the pulsar timing. So it doesn't dip down into these regions where they expect a detection until the they've got 2015 here and 2020 time frame. So that's going to be happening pretty soon. So hopefully in the next few years we hear detections from these ones. And looking at these supermassive black holes is a real critical thing in astronomy, because galaxies are built up by these supermassive black holes that form originally in these smaller galaxies, and they eventually coalesce to form larger and larger galaxies. And we want to know about that history of how black holes continue to evolve over time, and this will be a mechanism to do that. Okay, here's this nice video that they made of the two black holes that were, and this is what you would see if you were able to see it up close and personal. And it's slowed down by a factor of 100 in time. So these things were whizzing around at nearly the speed of light, and when they coalesce and touch, that's what they do. So you see it's very at the very end, it's just very quiescent there. So it's kind of neat on the gravity waves where they have this very violent last little step, and then the waters are still after that. So just the signal just actually goes flat. Now that's what you would have seen if you got close to it. Now you might have seen in some of the articles on this detection, this is our only mechanism of really probing what's going on in the black hole. We're never going to see them like we saw in that video there. But that's not quite true. We have the abilities to see a few black holes. So I wanted to talk to you about a telescope that's called the Event Horizon Telescope, which I've talked to you before at, but it was Farrell Ozol gave a talk at the American Astronomical Society meeting last January, which I wanted to talk about last month, but I'm glad I saved it for now. And she shared her slides with me here. And anyway, the Event Horizon Telescope will have the capabilities to see a couple of black holes down to the event horizon. Well, what kind of telescope is it? Well, first it's a radio telescope. So it's looking at radio light, but it's creating images with radio light, just like we create images with our eye in the visible part of the spectrum. And the radio light has the ability to actually see into very dusty regions where you might expect black holes to be. In this case, we're going to be looking into our own galactic center and another very massive black hole in another galaxy. So it can peer down into that, and so it sees through that dust. But at the radio part of the spectrum, to get really good resolution, in other words, to see really fine detail, you have to have a really, really big telescope. That's right, radio telescopes like the Arecibo ones are really big dishes. If anyone's been down to the Very Large Array, that's a big dish as well. Well, none of those are big enough to try to image the center of our galaxy and the black hole that lurks there. We need a telescope that is as big as the Earth. And so the Event Horizon Telescope is a bunch of telescopes around the Earth, radio telescopes here. And so here is kind of an image of some of all the telescopes that are going to be used there. And the big one that Dr. Olzel had announced during the meeting was the fact that the South Pole Telescope has joined that consortium. And it's very significant. Here's the South Pole telescope down there because of the mapping it gets you from the sky. And so here is actually a couple of views where there are locations of radio telescopes on the Earth here. And here's the south one there. And so what it really gives you is a lot of coverage in the north-south direction here. And this is actually the view of the Earth from looking back at the galactic center. You had a question?
Yeah, could you point to the one in the Canary Islands?
Well, they're not showing that. Canary Islands would be out over in here. So that's not one of the ones that they're showing. So there's still radio telescopes that are actually joining this consortium. Another big one, of course, is the one out in the Atacama Desert here. There they have a bunch of radio telescopes because they're looking in the millimeter part of the spectrum here. So you need a lot of these, but you can see viewing this from this angle that you have telescopes that span the entire Earth. And that will give us the resolution that we need there. So there are two objects that we can see down to the event horizon from our perspective. One is in the center of our own Milky Way galaxy, which is 25,000 light years away in an area we call Sagittarius A. And that black hole that's down in there is about 4 million times the mass of the sun. Okay, turns out it's a pretty wimpy size black hole, but it's the largest one we have in our Milky Way galaxy, and it's by far obviously the closest massive one there. So we're going to get the best resolution of this particular one when we stare down. And then when you're looking at the center of the galaxy, you need to look at wavelengths in which you have the ability to penetrate all this gas and dust that's blocking your view. So we have no hope of looking down in the visible part of the spectrum at the black hole that lurks down there. These are actually infrared images, or these are radio images here as well. And the other one is the center of a giant elliptical galaxy called M87. It's 50 million light years away, yet it harbors a black hole that's 3 billion times the mass of the sun. And therefore, we have so the bigger the black hole, the bigger its size. And in fact, it actually grows linearly with the size of the black hole. So a black hole that's twice as massive is twice as big.
A question about when we have volcanoes that go off like the ones in Greenland or Iceland will that interfere with the radio readings, or do they know how to compensate for that?
The radio telescopes aren't affected by any shaking motions and stuff. Now, the LIGO is affected by anything that's going on Earth. And in fact, that's an amazing thing that they can isolate those masses to that extent that they can measure 1/1000th of a proton without getting vibration. Because you've got to hold it up, right? You got to hold up those masses there. So the suspension, that's been the critical thing on those.
Well, that's not just the vibration of the
Oh, you mean like the dust in the atmosphere from that? Oh, yeah. So this is dust that's out in our galaxy, and that's minuscule compared to how much dust there's actually between there. So that radios can see through that part of the spectrum, and radios can see through clouds as well. That's why they don't really care that much about those. And so there's a tremendous effort actually going on, a theoretical effort where we are modeling how these black holes will actually look when we point this telescope, which we hope to do in the next few years, where we should be able to image the center of our galaxy. And so they're looking at lots amounts of parameter space in terms of different radio wavelengths, looking at different what we call accretion models. Our supermassive black hole at the center of the galaxy is eating a little bit of material, but it's pretty inactive. There's not a lot of stuff going on there. But as that accretes there, you get various things that are going on. And here's one of the models. I won't show you all of them, but here's one of them where it is going to look at different inclination angles. This is 30 degrees from the spin axis here. Notice here now we're at 108. They'll go to 90 degrees, which is edge on right there, and you can see it's something splitting. Notice that you see a bright region over here. This is kind of the event horizon. It's about actually 5 event horizon radiuses out where you see this effect, which they call the black hole shadow and everything. And so looking at different angles here, looking at the accretion of materials onto the black hole and whether you could see through them, and you can do that. They've got massive supercomputers working on these simulations. And of course, we're looking at different angles because we actually don't know our black hole, what degree it's, what angle it's actually spinning on. It doesn't have anything to do necessarily with the spin axis of what the stars are going around the center of the Milky Way. So those are really cool. So the things that they think that they can measure, one is this black hole shadow. So you get brightening on one side versus the other. And this side here where you get the brightening shows the rotation. The rotation is actually coming toward you here and away from you there. It's the same kind of effect of the frame dragging that I was talking about, that Earth. It's dragging space along with it. So therefore the photons of light that are emitted from this side over here can are brightened as well as shifted more to the blue end of the spectrum as they come over here versus the ones that are over there. So we expect to see this, and that whole thing kind of highlights this shadow, this black region in which you are really peering on to the black hole. So that's one of the things we'll be able to see. And here's, with what we think we have the capabilities by 2018, here's the simulated image of how it will actually look, and here is how we would, it's also a simulated image, and since we don't have the telescope, but given the resolution and resolving power of the Event Horizon Telescope, how that object will actually look. Very exciting to be able to see that. The other things that we'll be able to see is any kind of accretion flow onto it. As our black hole starts to suck up material, it'll create these hot spots and things like that, and we'll be able to see those as flaring things if we are able to indeed image down to the event horizon. Okay, so I'll just leave you with this last image here, which I showed at the beginning, her slide. But this is not art, even though it's pretty and everything, but it's just another shot from one of these simulations of how the black hole will look when we eventually get to see it. Okay, so anyway, that's actually all I have today. I want to make a few announcements. One, for those of you who don't know, we post a tape of this talk on our website here, and we also give a few links of some of the better websites to go to if you want to do some more exploration of this particular exciting, momentous occasion in astronomy and physics or whatever. These don't happen very often, so it's very exciting times. Also wanted to announce a talk that we have coming up March 2nd. So the talk is called Coloring the Universe. You might have got some flyers on this particular talk. This is going to be shown in IMAX. It was forgotten to put registration information on those flyers. So you need to make sure you go, if you want to go to that, register online or call in if you want to go to that event. But we're also, this person who's giving this talk is also going to do a planetarium show about showing aurora above Alaska here. And that planetarium show is going to be a free event. It's going to be at 4:15 to 5:15 here. So for those of you who are members, you obviously can get in and everything that is free. But if you're not a member, you won't be able to get into there without paying admission if you want to go see that event. And of course, it'll end at 5:15. So you want to, it'll be after the museum actually closes. Yeah.
Who is that person?
Actually, this is a person that Kachun Yu knows and everything. So who I'm going to go to the talk as well. I don't know much about him. So So, Color in the Universe is about how do we actually produce, I think, the pretty pictures that we see from Hubble and things like that. How do we actually go through that process? So, it should be a really good talk. Okay, and then the next 60 minutes is going to be on March 30th. So, hope you all can come to that, and I thank you very much for your time.